So welcome everybody for this webinar session. Today we're going to talk a bit about our line of ceramic and metal filament and go through a practical demonstration of how we use these materials and how you can use them to manufacture your parts. So I will share my screen to show you some presentation. Of course, this is an interactive webinar. So if you have any questions, you should put them in a Q&A session. I will either try to answer them directly or answer them at the end of the presentation. Before we start, just a few words of introduction for those who don't know Nanoe or myself. So I am Guillaume De Calan, the CEO of Nanoe. And Nanoe, we are a material company. We've been active for more than 15 years, and we're producing ceramic and also metal raw materials for that period of time for industrial processes. So we're not dedicated solely to 3D printing. We also manufacture materials for more traditional process. It's an industrial company with a production center and an R&D center with 10 people dedicated to R&D development of new products in the company. Most of these new products are now dedicated to our branch of material for 3D printing, which again is just one part of the activity, but where we are trying to innovate at the moment. So a few years ago, it's a bit more recent, it was 2018 when we started developing materials for 3D printing, and what we offer to the market is a line of ceramic and metal filaments. Ceramic being mainly alumina, zirconia, and silicon carbide ceramics, and the metal filaments being stainless and tool steel. We also offer a whole range of equipments to use these filaments. So we're not equipment manufacturers, but we quickly found out that most of our customers required us to offer a full package so that they could really start printing, debinding and sintering our material as quickly and as smoothly as possible. So we do offer equipments that are not manufactured at Nanoe, but we work with partners for such equipments. Just a very quick word about the technology, and we'll dive more in details afterwards. The filament we manufacture are actually, we talk about ceramic and metal filament. We actually manufacture composites. That means a filament that is usually a mixture of a ceramic or a metal powder and some binders that will help to shape the part. This obviously means, and again, we're going to dive into detail of this in the presentation, but this obviously means that to get to a final ceramic or metal part, you need to have a post-process to remove those binders. And that's, let's say, that's the magic trick that allows us to make a ceramic filament. Of course, if it was pure ceramic, making a filament out of it would be difficult. So why did we choose that technology? Why did we choose to develop FDM instead of other technologies which are on the market? For us, it brings a few distinctive advantage for that market. The first one is that it's a really low-cost investment technology. It allows to break a bit the price barrier, and it's also a very easy-to-use technology. And that really solved the main pain point we saw on the ceramic 3D printing market. Metal is a bit different, but ceramic, there is still a very low adoption of ceramic 3D printing for the moment. And we feel that one of the reasons is that precisely there are very few equipments available on the market, and that these dedicated printers are usually extremely expensive and quite complex to use. And mainly directed at let's say very industrial applications where you can afford such printers and such complexity. We on the other side wanted to develop a technology that allows to democratize ceramic and metal 3D printing. So that's what we're doing, and the way of doing that is precisely, instead of having a dedicated printer for ceramic and metal, we use standard FDM, FFF printers from the market, and we just add our filament into it. That makes the technology, of course, low cost. It makes it quite easy to use, while still keeping the properties of the material. So if you have a ceramic, you'll still have the hardness, the heat resistance, and so on. And if you have a metal, you will still have the tenacity, and the strength of the metal. And of course, the advantage of 3D printing in terms of complexity, small volume production, and all that. Final word of introduction before we go to the actual demonstration of the technology. We also developed last year, we launched a line of dielectric filament. It's again a line of filament with a ceramic filler in the material, but the main difference is that it's not designed to be sintered, to be post-processed afterwards. So it's a very specific material. It's dedicated only for radio frequency, so radar and telecommunication applications. I'm not going to dive into details of this material today. I know that some of you might have interest in dielectric materials. We may do a second webinar on this. However, ceramics are also extremely good dielectric materials, so you may still find some interest in the demo we're going to present today. But the only thing to remember from this is, well, the process for these materials is very different. The principle is the same. You have a ceramic filament, but the process is extremely different. And especially you don't have any sintering step. So now let's dive a bit into the technology. How does it work and how each of these steps works? The idea of this presentation is really to cut down every step by step, all the process, so that you really see how that works, and that you can understand better, and maybe remove some reservation you may have about the technology. We're going to try to be transparent also about what can happen wrong in the process, so that you understand what are the key points you should be looking at. So the first thing is a global overview of what we're going to see today. And when we do ceramic materials, we usually have, well, let's say 4 main steps that we're going to see today. File preparation, which is also called slicing, printing, debinding, and sintering. Sintering is done under air for ceramics. If we switch to metal, then it is very similar, except that you don't necessarily have a debinding step, at least not a chemical debinding step. It does depend on products. And the main difference is that sintering is done under argon, which is really quite different. And we'll show a bit of details about this in the process. So let's start by file preparation. To be honest, that's where we're going to spend the most time, because most of the success of the full process is linked to how you're going to prepare your files. If your file is well prepared, and if also your design is adapted to ceramic and metal 3D printing by FFF, once you've printed the part, you shouldn't have any surprises. You shouldn't. But again, that requires to understand what are the key elements of file preparation, and then it also requires to respect design rules. So I'm going to actually go out of my presentation and actually open the software we're using for file preparation, the slicer, so that you can really see how that works. So here we go. We'll start with a very simple part so that you can see a bit how that looks like, and then we'll go into more details. So here you have an example of a part we're printing very often at Nanoe. It's one of our demo parts. It's a small ring with the Zeta for Zetamix, which is our brand for ceramic and metal filaments. This is a ring we really print quite often. It's an interesting demonstration for us. We have opened it into a slicer which is called ID Maker. It's the slicer of Raise 3D, which is one of the brands we're working with. Of course, we could use different slicers such as Cura or others. Really, this would be similar. So you can visualize here the actual printing space we have, which is quite big on this printer. It's a 30 by 30 by 30 centimeter plate. So of course, if we were printing rings, we could consider actually printing several ones. Just by copy paste, you can create the second one and the third one and so on. Here, the interest is not necessarily to print hundreds, it's just to show you, but so I'm going to suppress these, but of course, if you have a big plate, you should probably use it. So once we have the part in the slicer, the first thing we're going to do is scale it. That means we're going to print it bigger than the size we actually need, because we're going to have a shrinkage doing sintering and we need to compensate for it. So these datas of the exact shrinking rate you need to apply are indicated in the data sheets of our products. I might actually show you if I can do that in parallel with the presentation. You go on our website, zetamix.com or zetamix.fr. You click on the filament you want to use. Today we're going to make the demonstration with black zirconia. So let's go for black zirconia, and here you will have lots of documentation, a user guide, a data sheet, a design guide, and a safety data sheet. So you could use either the data sheet or the user guide. We're going to just click on the data sheet. I think that's should be enough. And you'll have a few information about the filament, and the data we're looking for is the shrinkage. And I'm quite wrong, it's not indicated very clearly here. It is written here, but actually we'll go into the user guide where you'll have it written more clearly on the scale factor. The scale you need to apply to the part is 127.4 for black zirconia. So I go to my part and I say that I want to increase it by 127.4, and that's it. This is a size we need to print if we want to have the right dimension at the end. So if I want to prepare the file, the first approach is quite simple. I could just go, sorry, I went a bit quickly, on start slicing, use a predefined set of parameters, click on slice, and that's it. The part is ready to be printed. So I can go and have a look at it, see how much time and material it requires. Here's 1 hour for that print. It's a bit long, but probably the printing setups are relatively slow. We could probably do a bit faster, but for a basic print, that's fine. I'll immediately draw your attention to one thing, and then we're going to go into the more detailed parameters of slicing. In that part, which is a preview of exactly how the part is going to be printed, you can already see layers if you zoom a bit. These layers here are the way 3D printing works. You know, you're cutting the part in layers, in layers of typically usually 100 micron. If I dive into the print, I'll see several different colors. I see a red contour, I see a green one, I see some yellow infill, and I also see a bit of orange. All of these are different zones of the print. So usually when you print with FDM, you are always going to start by printing the outside of the part, the contour, what we call the shell. And here we've decided to print two shells, the red and the green, on each side. We do that to have a more precise print and a better surface finish. And then we will fill the inside, and we can decide to fill it completely dense, or just like it is here, to fill it with a porous structure. That's really a choice. And on the top and the bottom of the part, you will usually, to make sure that you have something completely closed, you will print what we call a solid fill, just to make sure that the bottom and the top are completely closed. So that's the first thing. We offer, with the material, we also have preset profiles. You can use them directly, no question to ask. It's pretty simple, and that's it. So now if you want to dive into more details, you'll basically see that there are a few key parameters. It was written on the slide. The main parameters that are important and that you may play with, we usually say there's around 10 parameters. So if I go back into start slicing, instead of clicking directly to slice, I can either edit or just double click on it. I will have access to all the advanced settings. As you can see, there are literally hundreds of them because you have a lot of different parameters and a lot of different tabs here. So you can really play on hundreds of different parameters, all of them being really relevant. I mean, they all do have an advantage and an interest. But for the sake of simplifying and of not keeping you for 2 or 3 hours in a row, I'm not going to detail all of them, just the main ones, the 10 main ones. The first one is very obviously the layer height. So basically, I'm going to slice my part into layers. How big are those parts? We usually use 0.1 millimeter for ceramic and metal prints. We could do smaller, but we're a bit in the limit of FDM precision. We sometimes do bigger if we have very big prints, sometimes go to 0.2, but 0.1 is really a comfortable number for us, and we usually stick to that. It's usually a good compromise also between print quality and time. I did mention the shell, the fact that we're starting by printing the outside of the part so that we have a nice surface, and then we fill the inside. So the number of shell is also a critical parameter, of course, and here we have set it up to 2, which is probably a standard choice, even though it may depend if you need a thick shell or not, depending on, do you need a strong part, do you need it light, are there some specificities, do you need it to be watertight or not, and so on and so on. But the normal setup would be probably 2 shells. And we'll go to the extruder, where we also have 2 very important setups, the extrusion width and the retraction. The extrusion width is, of course, linked to the nozzle size you're going to use. Usually on our printers, we usually use 0.4 or 0.6 millimeter nozzles. We've printed with smaller, we've printed with bigger, but usually, again, 0.4 to 0.6 is the right compromise. And one of the important things is that even if you have the 0.4 millimeter nozzle, you may choose to have an extrusion width which is slightly bigger than the nozzle. And we actually usually recommend it. We recommend to print with a slight over extrusion, which is better for the adhesion between layers. So typically, if you have a 0.44 nozzle, we would print with a width of 0.44. Retraction is also very important. Retraction allows you to make travels between 2 zones of the print where you don't print, and to avoid having any leakage of material, what we also call oozing sometimes. So to avoid the material oozing from the nozzle because it's melted, you actually retract a bit the filament to make sure it doesn't come out where you don't need that. So it's important for some prints. For some prints, you may completely deactivate here, but for most prints, we would recommend using a retraction. The only thing is we're going to be quite careful about retraction speed, probably lower it a bit so that we really have a smooth retraction. the one thing you need to remember about this filament is that they are relatively brittle, they are fragile, and so if you print very fast and then retract very fast and then reprint very fast, you may break the filament. So we always try to be quite gentle with the filament, and typically on retraction we would be relatively slow. So that's the two main ones on the extruder. Then there is the infill, which is of course very important. We have a few things to choose here. The infill density, the extruder we're using, usually we use the same material, of course. The infill density, you may choose to put it to between 30 and how high you may like. Less than 30 is usually difficult afterwards to actually print the top of the part, so we don't recommend to do less than 30. And the shape of the infill is important also. So you can make grids, honeycombs, whatever. We usually do like to use a gyroid infill because it is relatively isotropic, and that's for most prints it's preferable. But again, that's really a choice. Once we've seen that, you'll have the solid fill where you just define the number of layers you want to be completely fully dense on the top and the bottom so that your part is closed. Sometimes you may choose to have a part which is open on the top or on the bottom. It's actually very favorable for debinding, so sometimes we just choose to leave it open, in which case you just put 0. But well, that certainly does depend on the part you want to print. We'll talk about support later on, so I'm just skipping this one. The part we have for the moment doesn't need any supports. Platform addition is also not necessarily the most important thing here. Cooling is quite important, but the settings are pretty simple. We usually, for ceramic and metal, try to cool quite effectively, starting at a second layer. So why do we need to cool the part? It's because, of course, you're melting the material to deposit it. If you want it to keep its shape afterwards, it needs to cool down as fast as possible. And here we will have a difficulty, which is you'll see just afterwards, but we're printing at relatively low temperature because the material softens at very low temperatures. So if we want it to retain its shapes afterwards, we really need to cool efficiently once it's outside of the nozzle. So we'll just put the fans to 100%. So temperature depends on the filament. It's also in the data sheets that I just showed on our website, which is really where you should look for information. And that's where they are updated every time we have a new version. So the printing temperature for black zirconia is 180, and the plate temperature is 60 degrees Celsius. This is not an absolutely compulsory thing to have a heated plate, but if you have that option, we usually heat it up a bit. It improves a bit plate adhesion. Speed is important, of course. We usually print at relatively slow speeds, so that certainly depends on your part. If you have big parts, you may want to increase that. You could go to 40, maybe 50 millimeter per second. But as a first setup, 20 millimeter per second for every way is usually fine. And I would say that's it for the moment. The rest are really advanced setups, and I'm not sure you necessarily need to know about these. Once you have filed in all of your information, you click on OK, you click on Slice, and that's it. You have prepared your print. You can preview it just to check exactly if everything is happening as you would expect it. Here the print looks good, and then you can just export it either directly to your printer or to a USB stick, and you just launch the print. So that's it for the basic parameters. Of course, this part was very simple. You're probably going to ask about a lot of questions on support and all that. I already see a few Q&A questions. I might actually have a look and see what are the questions. Some of them are probably answered later on, so I'll keep them for later, the questions. But you should really feel free to keep asking. So that's really the basic steps. Then you may have a few other considerations to look. The first one is probably supports. That's something that will happen quite often. You need supports because you need them for printing, and sometimes you also need them for sintering. So of course, if I want to do supports, I will need to have a more complex part because my part is too simple. You don't need support here. I'm going to delete that one and open a new file. Import model. That's here. Wait a minute. I think it's going to be more simple to do it that way because I know where the part is. Here we go. So this is a demonstration part we're using quite often, precisely because it does show a few of the difficulties we may have. You have some holes, you'll have some supports, you have some cavities, and you'll have to think about how to print them. So the first thing, of course, is how do I choose to orient that part on the plate? How do I put it on the plate? Well, here it's obviously pretty straightforward. I'll have to rotate it. No, not that way. Here. I'll have to rotate it so that I have something which seems logical. But of course, there's going to be a few problems here. This part here that you can see here, it's a 90-degree angle. Well, I'm afraid I can't print over air, so I will need some supports here. This one also will need some. You have a few cavities below that also need some supports. The other ones will should be acceptable. Again, you have some rules to define this. You have holes also, and these holes pose the same question: do I need supports or not? So we're going to talk a bit about support. The first thing again is I need to scale my part, so I will do that so that it's done. Right. And then I will add support. So there's a few ways to do that. The first one is you can use the support section here, which will allow you to generate these supports automatically. You can choose from which overhang angle you want these. Let's say it's a 40-degree angle, and you can create auto supports. So you have supports here. Of course, you don't have on the other two ones because the angle is less than 50 degree. You have it here, and you have it in the holes. So you may decide to remove some. You may say, for instance, that very tiny hole, I know that we're actually going to manage to print it without supports, so I can remove them just by clicking on remove and manually removing the supports that are in the hole. Of course, I might have to turn apart to check that I've removed everything. I haven't. Here we are. You may do that on a bigger hole if you feel confident you might manage to remove those. So that's the general idea. I guess you understand what I mean. So the interest of generating this support at this stage is that you can control where they are. You can decide to put them or not, and that might be of interest. I'm going to clear them because I'm also going to show you another way to do that, which is the one we usually use. We usually don't place the supports manually. We just use a slicer to do that by giving this the right instructions. So we go back to start slicing. We'll go into the details of this slicer and supports. Here you can choose to add supports either from the platform or everywhere. Let us say here that I'm confident that I can print the hole without supports. In that case, I would choose to use just touch platform. You can choose if you're printing the support with the same material, in which case you're going to use a left extruder because we're printing the part with a left extruder, or with another material. You can choose the type of support, and we usually like to have support which are lines because they're easier to separate afterwards and to remove. Decide from which angle do we need to add supports. we usually say between 50 and 60 degree. Less than this angle or more than this angle, you can just print them and it's going to be completely okay. But yes, if you have more than 60 degree of overhang, you may need to add supports. So I click on OK, slice, and we should see supports appearing in the right places. And this one takes a bit longer. I'm afraid my computer is a bit slow at the moment. So these supports are really extremely important, of course, because without that you can't print a part, but you may also need to retain them for sintering. That's one of the crucial thing. Especially with metal, you may need to retain those supports for the sintering stage. I was not anticipating that my slicer would be so slow. Sorry about that. I guess it's going to come in a minute. Here we are. So you can see that we have supports here, which should be the case. We have supports here. We also have support there, here and there in the small cavities. If we zoom on how the supports are made, you can see that these are actually lines which are adjacent. This is interesting because it makes it relatively easy to remove either before or after sintering. You just take a pincer and pull them out, or with a flat tool you can just separate them. It's relatively easy to remove, which is why we like that kind of supports. And the rest of the parts is again really very similar. If we dive into the part, we're going to see the infill in yellow, the shells in green and red, and you can see here really the heart of the part with support on both sides, the infill, and well, everything looks okay for me. So that's it for supports. There are a few other things, things that might be seen. Oh yeah, I was going to forget. So I did mention that supports are of course necessary for printing. You have an example here for a ceramic and for a metal part. It's also quite often necessary for sintering, especially in a case where you have a lot of weight. If you take the ceramic example, for instance, the part was printed and sintered in that direction. It was more simple for printing. It allowed, it removed lots of supports, of course, but that meant you had a quite massive zone here on top of the print, and if you don't want any deformation during sintering, you should keep the supports for sintering. Again, they are relatively easy to remove afterwards. We just use a screwdriver and remove them in a matter of a minute. That was really very easy. But we did keep those supports, the big ones here, and also the ones below the small elements there. For metal, it's even more crucial because metal is sintered at a temperature which is really very, very close to the softening temperature of metal and even the melting temperature of metal. So the metal is literally soft when you're at sintering temperature. So you need those supports to stay there during sintering if you have significant overhangs. In some cases, you may need to use a release material between the support and the part to avoid the part sticking to the support. We have a few methods to do that. We can use, of course, a ceramic filament, but more simply, we usually just put a bit of ceramic powder between the support and the part, and that really works very well. There are a few other things that might be noted at this stage, which are linked to print preparation and some things that you should take into account if you want to avoid deformation and cracks during the rest of the process. The first one is we need to avoid high thicknesses. If you have a very high thickness in a part of a fully dense material, you take the risk of having cracks. So typically we usually say more than 10 millimeter of fully dense wall is really hard to achieve, and we prefer to stay below 5 millimeter. Actually, 5 is our recommendation. That means if you have a wall or an element of your part that is more than 5 millimeter, we usually print it with infill to avoid those cracks and deformation. So that the solvent can actually get into it, it's even more favorable. So when we have the choice, when we can leave the infill open in some way or accessible to the solvent, we do it. So sometimes it can be just 2 small holes. Sometimes it can even be one part of the top or the bottom of the part which is completely open. That's even more favorable and makes for faster debind and sinter. It's not necessarily, however, you can close the top and bottom and still debind the part if you respect this 5 millimeter limit. It's just gonna take a bit longer for the solvent to reach inside the part. If possible, we should avoid sharp angles. 90-degree angles are usually favorable places for cracks to occur. If you look at the part which is in the illustration here, typically on each step we would try to add chamfers to avoid a sharp 90-degree angle. That would be really more favorable. We should avoid significant changes in thickness. Having a very big thickness at one part of the print and a small thickness at another part is risky, and especially it's risky for deformation. You may have deformation. And if you are printing thin walls, you should activate an option which is in the slicer. It's a bit technical, so I'm not sure I'm going to show you today, but this is usually part of our more advanced demo, and you can find them probably on our YouTube channel. There is some options to activate printing that will change direction every layer, so that you actually print one layer clockwise and the second one anti-clockwise. If you don't do that, you risk having deformation on thin walls. So that's something we also recommend if you have thin walls on your part. The last thing also is you may have porosity in your print, and that's something very typical of FDM, FFF prints. We usually see that kind of defects if you're not printing dense enough. Here on the center part, you can see a part that has clearly be under extruded, so there's not enough material, make it simple. So that can be corrected with some setups on flow rate. This one is clearly under extruded, so we should increase the flow rate. Flow rate is usually for our material to more than 100%, 105, sometimes 110%, to make sure you're fully dense. Of course, that's very important for the mechanical strength of the part. And you may also have defects which are only on one part of the, on one zone of the print, which is typically what you can see here. The rest of the print is relatively dense. You do have a crack here, which is probably linked to that porosity, and you have nice aligned porosities here, which are between the shell that we printed first and the infill. This again can be corrected by another parameter, which is called infill overlap, which basically says how much does the infill needs to go over the shell so that the connection is fully dense. And so you need to increase that from maybe 20% up to 50, 60, 70%, depending on the prints and how dense you need your part to be. So that's it for print preparation. Again, this is where we spend more time because this is actually crucial. If you prepare your print correctly, if you respect the guidelines on thickness and on the other elements I noted, some of them are actually more a design question, but let's say if you prepare your design and then your print correctly, you shouldn't have any problem doing printing and debinding and sintering. So printing is very straightforward. It's very similar to normal FDM, so I'm going to go quite quickly on this, just to remind that you need to be careful about having a proper first layer, that it needs to be perfectly aligned. you need to load the filament and then launch your print. I'm actually going to accelerate a bit on this because this is a demonstration of what we usually do when we print with our material with an old printer, which is called the Race 3D Pro 2. The new one is a bit dated from this one. So you can see here that the spool is placed on top of the printer. That's the one modification we do to most printers. The filament is relatively brittle, so having it directly on top of the extruder is more favorable. You can also see that during manipulation, the operator is quite careful at that stage. Again, the filament is brittle. The moment where you risk more breaking it is actually when you manipulate it. So we're careful at that stage. Well, you can see that here he's inserting the filament. This is really, fairly straightforward thing. We've opened it so that you can see what happens when you load. The extruder will start turning and will push the filament through the nozzle. That's really fairly straightforward. We usually don't open for loading the filament. It's just to illustrate here how that works. So you close, you screw it. One of the crucial thing with most printer is how tight will we set this screw, this extruding screw. Does need to be sufficiently tight to allow for the printing process to happen, but not too much because you may crush the filament. So this setup on that screw is quite important. Then you need to do the bed leveling. On most modern printers, no, it's the case of the Pro 3 that we're using now. This is automatic, so I'm going to skip a bit this. But if you don't have an automatic bed leveling, having a good bed leveling is really important. So here we're just loading the filament, making sure that it's completely inside the nozzle, that there's no air remaining and nothing. And so here we're doing the bed leveling, but I guess I can skip that. Yeah. Again, most printers now use an automatic bed leveling, so you don't need to check that. It's quite important, of course, if you want to use the full surface of the print, that the full surface is flat. If you have to do that manually, it's a bit tedious, so that's why most printers now have a probe that will check if the bed is flat and compensate for small unevenness. And we usually will favor that when possible. Well, once this is done, it's really, really very straightforward. We'll just launch a print and then remove the part from the print. So here you see, well, printing is really straightforward. Once you have done this, well, I guess this is I hope an accelerated version, because the print, this one probably lasted a bit less than what I showed you, but something in the range of half an hour. And once the part is printed, to remove the part, we usually use flexible beds so that it's easier to remove the part from the bed. One of the very important things is, again, these materials print at low temperature, and they're quite soft, which means if you don't want any deformation when you remove the part from the print, you need to wait until it's properly cooled down. That's really important. And then once you have the part printed, you'll go to debinding and sintering. This explains a bit what's happening in the process. Most of our filaments use a two-step debinding process. That means chemical debinding and then thermal debinding. Chemical debinding is done with acetone, and thermal debinding is done in the furnace just before sintering. What happens actually is that in our filament, you have several binders. You have a backbone and a soluble binder. The soluble binder will be removed during the first step. That helps a lot the following process, because the first thing is it removes half of the binder, and it also creates a network of porosity that will help you remove the rest of the binder, which is actually going to be burnt out, and so the gases of this burnout can come out of the part more easily. This is usually if you have cracks, you'll usually see them already in the solvent extraction, and if not, you'll see them afterwards in thermal decomposition. But usually you see them already during solvent extraction. And if you have cracks, that usually means you haven't made a complete debinding. And you still have too much binder in the part when you remove it. So there are some strategies here, but the simple one is to remember that usually you never debind too much. So we will keep the part in the bath as long as necessary, and if it needs to be longer, it's fine. So we usually say that mass loss should be more than 5%. It does depend on filament. So actually every filament has a dedicated recommendation. And at least we really recommend you to measure the mass loss to make sure you've removed enough of the soluble binder before going to the next stage. Well, the way it works is really very, very simple. We use ultrasonic baths. We actually don't use the ultrasonic. We just use it because if you want to speed up the process, you may heat up a bit the acetone. So we put the part in the case, in the basket. We put the basket in acetone. Usually when we put the part in acetone, the acetone is cold. We'll close and heat up. So we just launch the heat just before opening, but that's similar. You have to wait for a few hours. Sorry about that. You have to wait for a few hours, and then you can just remove the part. If the part is really massive, if you're worried about cracks, sometimes we also cool down the acetone before removing the part. This avoids some cracks appearing during the part dry out. Once you've done that, the part is going to dry relatively quickly because acetone is very volatile, but you do need to wait maybe for 1 hour, and then you can go to debinding and sintering. Just a few remarks here. This is a part before and after debinding. You can see that there's already a bit of shrinkage. It's minor, but still it's here. And there's a change in color, which is completely normal, but it's good to know so that you're not worried about that later on. So sintering, what happens during sintering? So that's usually the bit of the mystery part for most of our customers who are not experts in ceramic material. So it is a bit counterintuitive, but sintering is a process where we will densify the part without melting, of course. We want to retain the shape of our part, so we won't melt. We will just use a solid diffusion at high temperature to densify the part. We typically go from a part which is after debinding very porous, of course. It has between 40 and 50% of porosity, to a part which is a lot denser, between 90 and 99% density. Ceramics is 99. Metal is usually 95. Does depend a bit on the sintering process, but that's the usual value, which implies the shrinkage we were mentioning, the shrinkage of 15 to 20%, which is very significant and which is quite impressive when you see the part. So for sintering, we usually use either tubular or chamber furnace. We do offer both of them. The interest of chamber furnaces is they're much more convenient, but the drawback is that you can't sinter metal in it. You can only sinter ceramics. With sintering temperatures between actually 1,350 to 1,550. And the atmosphere is air for ceramic and usually argon or hydrogenated argon for metals. We have an example here. Again, I might accelerate a bit. So you program your furnace. It's already programmed actually, so that's pretty straightforward. You place your part on a setter. You put it in the tube if you're using a tubular furnace. If it's a chamber furnace, you just open the door and put the part in it. It's a bit more simple. You push it to the middle of the furnace with a dedicated tool that a small pusher rod that we supply, of course. You add some heat shields, some blocks that protect the tube and the furnace that actually keep the heat inside the hot zone. And then you just close the lid and that's it. You're ready to go. If you do ceramics, you actually don't necessarily need to close this. You can keep it open anyway. We're not going to flow it with gas. The process is quite long. It takes approximately 2 days. And at the end of it, you just open your furnace, make sure the part is cold before taking it out, or you can use protective gloves, of course. You use the same tool to remove these heat blocks and then to get your parts. That is really fairly simple. I guess we're gonna use a sintered part. Yeah. Yeah, that's it. So this is how it looks after sintering. So you see here, there is a significant shrinkage. That's where most of the shrinkage will happen. If we're interested in metal, the process is again similar, but with a small difference, which is we need to flow the chamber with argon. So the beginning is the same. We just push the part in the middle of the furnace. We put the heat blocks, but then we will have to close the tube and we will put it under a neutral gas, which is what you're going to see very quickly. You can see a bottle of gas in the background, which is the bottle we're going to use for this sintering cycle. So we put the flange that allows to put it under vacuum or under gas. We usually don't use tube, but apart from that, we don't use vacuum. Might have accelerated that a bit, but anyway. So here you can see we have a vacuum pump. We can use it for flushing the atmosphere at the beginning. Actually, it's optional. We don't always do it because anyway, the process is relatively long and we will flush the furnace during the process. You open your gas supply, which is usually hydrogenated argon. We put a slight overpressure of 0.2 bars. On the other side, you can see that it's closed at the moment. On the other side, we will put what we call a bubbler, which makes sure that you don't have any leakage, that you don't have oxygen coming the other way around. So on one side, you have the gas supply, and on the other side, you have this bubbler, which will guarantee that you have something which is completely gas tight. So the way this works is that you actually fill the bubbler with water, and you'll see that it allows for making sure that air doesn't go through in the wrong direction. This is crucial. You may think that just with the flow you can avoid having oxygen in the chamber, but having a completely neutral gas without any oxygen is difficult, and you really need that part to make sure you have the correct gas supply. And you can actually visualize the gas flow with the bubbles that are coming out of the bubbler. That does give you an indication, and then you can set up the precise value with that time was a bit fast with that flow meter that will give you the number of liters per minute, and we do give recommendation for sintering our metal parts. At the end of it, you close the bottle, you open on one side, and you can remove your part. Again, that's very, very straightforward. I guess we've seen most of it. You remove the heat blocks, and then you can remove the part, the sintered part. Right. And then, of course, you may choose to do some finishing, especially if you're using aesthetical parts. Ceramics are quite often polished, in which case we use tumbling a lot. It's a very convenient process. Metals, we usually use sandblasting, which is very efficient, just to have nice shiny, but we don't but that's not usually required by our customer. And so you have the part at the different steps of the process that really gives you an idea. So what are the takeaways of this? You can see from what we've shown you today that, well, step by step, this is relatively simple. Of course, you have those 3 steps, so that makes the process sometimes a bit complex compared to printing PLA, but still, as a process to make metal and ceramic, this is really the most simple process on the market. That's really what we want to bring to market, a simple technology, is easy to use. To give you an example, usually training takes 1 day. We sometimes do workshops where we invite people to come either at our place in Palaiseau in France, close to Paris, or we'll also do one, for instance, at the ESAS Congress in July, where we actually invite people to try, and in 2 hours you can have printed your first part. And that part will turn out well after sintering, really. So that's an easy to use process. That's the first thing. The second thing is it's low cost. A full package with printer, debinding, and sintering costs 15,000 euro, and that's really the public price. You can order it from our company, from our resellers, but that's the ballpark price for a complete system allowing you to print ceramic and metal parts. This is really unique. I mean, you don't have any other technology on the market that allows you to get that kind of part with such a low cost investment. And the third thing is it's quite versatile. You can use lots of different materials. Of course, it's still an FDM printer, so you can still print thermoplastics. You can print ceramics, alumina, zirconia, black zirconia, silicon carbide, which is a difficult ceramic to manufacture. You can also use steel. We also have other materials in development that might come out later on. All of this makes it a very versatile technology. And it still gets quite a good accuracy. So that was not the topic of today, but I'm sure it's going to come in the questions. What is the level of accuracy we can achieve with this technology? It does depend on materials. Some materials are more repeatable than others. Typically, ceramics are a bit more repeatable and reliable and simple to get around that metals. But still, all of these, you can get down to accuracy of plus minus 0.1 on a relatively small part. I'd be careful when saying that because it does depend on designs. Sometimes it does require an iteration to make sure of the shrinkage you have and to compensate for it before you get there. But that's, let's say, the limit value you could have. I think that's all, and I'm open to questions. I'm sure there are already a few ones, so yeah, I'll be happy to answer those questions. All right. We have a question from Dan about the margin of error for components. So, well, I guess I started answering a bit right now, but that could be a topic for a webinar in itself, accuracy of the technology. So that depends what we call accuracy. We do differentiate accuracy, repeatability, precision. All of these are different IDs. So there are a few things here. To give you an example, let's say tomorrow I want to print this part. You just saw it in the webinar. This one has been sintered. It's a 5 centimeter part. I've never done it. I print it for the first time. Just use standard procedures, standard shrinkage, nothing modified. I could end up well with a plus minus 0.1. Usually that does, but I could also have surprises because the shrinkage doesn't happen as it is supposed to. There's a bit of deformation or something like that, in which case I might end up with a plus minus 0.2, 0.3. In the worst case, sometimes 0.5, that happens. Even on a part which is just a few centimeters. It does depend a bit on the shape of the part. then if I go back, I say, okay, I've measured my part. I understood that the shrinkage for this part is a bit different. It's a bit more in XY and a bit less in Z, for instance, or something of that sort. If I go back to my file, compensate for this, and do a second print, I will get much closer to the final dimensions I'm requiring. And then once I have set up my process, I say, okay, I want this part, I want tenths of it, or 100 part, or whatever. So I repeat the same print with the same parameters, the same file, basically. Then the repeatability is going to be much better and will definitely, for part of that size, be in the range of plus minus 0.1, probably even a bit less than that. I hope that does answer the question. There was a question about acetone permeating using full infill. So yes, that's a risk, and that's a reason why we usually don't recommend using full infill, except if you really need it. If you need a fully dense part, well, we can try to do that, and there's a certain limit in thickness. But yes, we don't always recommend to use full infill. If possible, we do like to use an infill which is not 100% inside. It can be quite dense. We've made significantly big parts. To give you an example here, this part was done for a customer, and it's actually only infill, but the infill is 98%. So this does make for a very dense and very solid part, but the 2% of porosities are already enough to help for debinding. If I had to do this part of that size, you have a few centimeters per few centimeters fully dense, I would never do that by 3D printing. I couldn't do it. And 98% density we can, because we usually use those 2% of porosity to help for debinding and sintering. So there was a question about the kind of the kind of file we're using. I guess that's something about formats for 3D printing. Do we use text files or something similar? So basically, what the slicer does is precisely transform a 3D file, actually a surface file, so a STL file or a 3MF file, into a J-code. And what is a J-code? It's a list of instructions for the printer. So the printer basically doesn't actually see the 3D file. It just has a set of instructions going from point A to point B, then from point B to point C, and so on. So that's what the slicer, the software I used in the demonstration, is for. It's for transforming the 3D file into a set of instructions. Once you have that J-code, you can actually open it with any notepad or whatever, and you'll see lists of instructions. You can actually sometimes add manually a few instructions if you really need some very, very specific stuff. But yeah, usually we use J-code, and most printers use J-code. So is there a different material that can be a support in the sintering process? So for ceramic, we usually don't need that. We will use some supports. Sometimes we actually remove the support before sintering because it does behave well. Again, if I take my demo part here, this one, I'm pretty sure we removed the supports before sintering. It's not very heavy, so there was not too much deformation, and we could sinter it without supports. The same part in metal, you couldn't do that. But this one, you can remove the supports. If you need to keep the supports, they're actually going to come off quite easily. You just take a pincer afterwards, you grab the supports, you break them. The ceramics we're printing, zirconia is a strong material, but it's still brittle. So that means if you really go hard on them, you'll break them. So you just break them away, and they will be removed quite easily. Now, if you talk about metal, that's a different story, because even for such small parts, you will need to keep the supports for sintering. So the supports are usually same material, because we want to have the same shrinkage at the same time. So you can't choose completely different support, but what you can add is a few layers, 1 or 2 layers, between the support and the part with a different material to make sure that it doesn't stick. So we have a few ways of doing that. One of the ways is to use one of our ceramic filament as a support material. That's possible. To be honest, most of the case, we usually just separate the support and the part, put a bit of powder, of ceramic powder between the two, put back and put it in the sintering furnace because we find it more simple than to do dual head printing. It's just to simplify the process. So we either use the ceramic powder as a release agent or the ceramic filament. So we are having difficulty as the filament either slips or breaks during print. Do you have a value for tightness of the feeder? So that's really the one question. If I tight too much, I might break the filament. If I don't tighten enough, it might slip off. And there's also a problem, which is that if you're too much at the limit, it may work very well, but at some point in the process, because there's a vibration and all that, the screw may untight a bit and suddenly it starts slipping. So we don't necessarily have a tightness value. It's really something we appreciate manually. Again, on recent printers, you see more and more printers which don't have exactly that setup. They don't have a spring. They either have just one set preset tightness between the two gears, or sometimes a few different positions, but just a few ones. Which really simplifies matters. To give you an example, the demonstration was with a Ray 3D printer. The new Ray 3D Pro 3 printer doesn't have any screw, and that really simplifies matter and makes the process much more reliable. I guess my answer may not satisfy you because you may want to use the printer you already have. In that case, I may suggest also to play a bit with different kind of springs. Having a spring which has less force, and so you can push it a bit more without applying too much force might be of interest. What is the minimum height that the spool needs to be above the printer? So I'm not sure I have an exact value. It's just a question of how much bend it's going to have. It does depend on the printer and the printer setup. I think on the Ray 3D it's probably 30 centimeter high. What exact type of bed do you use? We use flexible beds, which is the one you can see here. We use flexible beds, as flexible as possible, because we usually don't have too much problem of adhesion to the bed. The material adhere very well. We actually have the reverse problem, which is the material is again a bit brittle before sintering, and so if you have difficulty removing it, you may damage the part when you remove it from the plate. So we use flexible plates, as flexible as possible. And the other thing is to remind, to keep in mind to avoid removing the part before it's cold. Is there a phase transition in zirconia? You are right. So that's a bit for advanced users. But yes, the zirconia we're using is what we call 3Y zirconia, zirconia with 3% molar of yttria. It's a zirconia that has a phase transition toughening mechanism from tetragonal to monoclinic. So the powder itself is already tetragonal, mainly tetragonal. Let's say when you sinter it, you go to tetragonal. It stays at tetragonal, but during the life cycle, if you have some mechanical aggression, it may transition to resist to these shocks. So there's a question about the SiC filament. So you're right. I'm sorry, I'm answering in English because some people are probably English speaking. The SiC filament is the one exception in our range of filament. We can't sinter SiC with the furnace we're selling at the moment because you need a sintering temperature of 2,200 degrees Celsius, which is very high. Most of our customers, they already have compatible furnaces with SiC. If you don't, for the moment, we don't offer furnaces compatible with SiC. What we can offer is a sintering service. And we can also recommend furnaces. However, the investment cost is a bit higher than a normal furnace. So there's a question here which is interesting about porosity. The porosity is an outcome of the process, so one can change the porosity. If so, would it change the dielectric property of the printed part? Yes. So that's one of the big advantage of printing dielectric material or ceramic material, which are dielectric materials. In the radio frequency application, which is you can tune the permittivity with just playing on the infill. I may actually show you an example of this. It was not really anticipated, but we're going to go back to the website. If you go on our website, zetamix.com or .fr, you have a whole set of applications, and there are an example which exactly describe what you're mentioning. So I'm trying to find it here. We did what we call dielectric resonator antenna in partnership with a laboratory called LEAT, where we are using zirconia, which is an interesting material because it has a very high permittivity. The permittivity of zirconia is 32. And the interest for our customer was to actually have a dielectric resonator with two different zones of permittivity. You had the big square is a bit less than 30, and the small squares needed to be much lower. And so we just tuned the permittivity with the level of porosity we printed. You can see here two zones with different porosities, and there are small holes as you may not see for the feed, the coaxial feed. But that gives you an idea of this. So yes, it's completely possible. That's a big interest of printing dielectric materials for RF. Of course, you need to make sure that the structure you're printing is much below the wavelengths of your part, typically 5 to 10 times smaller. But if that's the case, you will end up with an equivalent permittivity, which is basically in the middle of air and your material properties. Also, a conference from LEAT about this, and there's probably some proceedings somewhere, so you can find them if you look into this, and you'll see some detailed explanation of how that was done. That can be done, of course, with our ceramic material, which have very high permittivities. It can also be done with our dielectric materials, which have a bit lower permittivity in the range of 2 to 7 for the highest, 7.5. But still, it can be done also in those ranges with the dielectric filament. So is the resulting steel comparable to cold process or to cast steel? So unfortunately, not exactly. It's a sintered steel. It's comparable to what you would have with MIM, for instance, metal injection molding, but you still have a bit more porosity than what you would have with a cast steel or machine steel or a cold process steel. One of the reasons for that is that we decided to stay with sintering under argon, or potentially argon with a little bit of hydrogen, and we didn't switch to pure hydrogen, which is a compromise. It's a little bit less good for mechanical properties, but it makes for much more simple process and much more affordable furnaces. So we decided to stay that way. It's a bit below that, and it's closer to what you would have with MIM. So when exactly should the support removed for both ceramic and metal filaments? So I'm afraid the answer is going to be, it depends. For metal, we usually keep supports. All of the supports are kept for sintering, and we remove them afterwards. If you need support for printing, that means you need them for sintering. For ceramic, if you want a simple version, I would say keep the supports also. Anywhere, they're very simple to remove after sintering. If you want to dive into details, sometimes you can remove them before sintering, especially if you have I don't know, small supports in the hole and you're concerned about removing them afterwards, you may remove them before. But honestly, in most cases, you can remove them after sintering. That's more efficient. So a question about deformation, that happens only at the first layers after debinding or sintering. So you can have, I mean, you can have problems at honestly every step. Usually it goes back to file preparation and design rules. If you respect the design rules, if you respect the file preparation guidelines, you shouldn't have deformation. But I mean, if you don't, you may have problems of deformation. We usually see them more in the sintering step. Sometimes you can see deformation before that, but usually you see them in the sintering step. What is the largest size of parts you would recommend to manufacture with this method? The short answer is something which stays in the cube of 10 centimeter of 10 per 10 per 10. You could do bigger, especially if it's just in one dimension, but it's for more advanced users, and especially it may occur more deformation if you go to bigger sizes. So yeah, 10 per 10 per 10 is already a good start. Anyway, with metal, you're going to be a bit more limited than that because our furnace is smaller than that. Our furnace for metal is a tube furnace with a size of tube of bit more than 90 millimeter in internal diameter. So your part needs to fill into a tube. And then you have shrinkage, which means basically you'll be more limited in the range of, I think it's 7 per 7, a bit longer if you want, but that's the idea. So I'm facing issues for problems for printing tall parts. Well, there might be a few reasons here. It does depend on materials. It does depend on what's the issue. It is difficult to answer without more details. I think the best thing to do is to send us an email and we'll have a look into it. But right now it's hard to say. But clearly, the biggest the part is, the more challenging it is, both for printing, debinding, and sintering. So that's why we usually say you should start small and then go bigger. What is the accuracy of filament diameter? I'm not sure I have the data in mind right here. I know that on, let's say, production grade material, it's quite accurate, probably in the range of plus minus 0.05, but I do know that sometimes for materials that are a bit more experimental or producing smaller scales, it can be less precise than that. I must say I don't have the exact value here. It certainly is an important feature, and it must be written in the datasheets, I would say. Can you use isopropyl alcohol instead of acetone? I'm afraid not. You could use other solvents which are, let's say, sometimes used to replace acetone, such as methyl acetate is a potential candidate, even though acetone is really the most efficient one. But if you're not in a hurry, you could use, for instance, methyl acetate, but not alcohol, neither isopropanol or alcohol. Is composition of binders the same from one lot of rolls to another? Well, it does depend. We make some updates from time to time. We usually try to communicate on that, but there may be, depending on how long was your last material print compared to the, you might have some variation from time to time, especially on some materials. We've made several updates on alumina to a certain point of time. Now it's more stable, but there was some several updates because the printing behavior of alumina was not as good as zirconia, so we updated it a few times. I know that we're also preparing a major update of our 316L, which is released this month, but we will communicate on this. But to give you an example, I think Ziconia has been very, very stable for the last few years. Again, if I don't see the part, I'm not sure I can troubleshoot in direct. Really, the best thing is send us an email with pictures of your part. I mean, it is a bit the same question as before. Yeah, to be defined, to be checked, but I will need the file. Datasheet for H13 gives a show D of 40, but the filament does not exhibit that. I would say it should. I mean, it's measured on our side, so it should. Maybe you had, if you really had a problem, maybe you should send over some email, and we can check this out and replace the spool if it's not the case. But it should have a show hardness of 40. We're measuring it. Are the filament hygrophobic and needs to be kept dry? Yes, it's better. Well, it's not that they're extremely hygrophobic, but if it absorbs too much water at some point, it's going to pose a problem. So, I mean, when you're printing, it's not a problem. You don't need to keep it dry when you're printing. But if you pause between two prints, and if it's a long pause, we recommend to put it back into a sealed bag with some desiccant. That's better. Cool beds, engineering beds, or textured beds. I don't think that's very significant. We usually do use a heated plate, but apart from that, anything would work. So stainless. Well, actually, there's a major update of stainless in a few weeks. So this is why I didn't talk about it, because we're going to communicate about it later on. But I can do a bit of a spoiler here. Stainless, we're gonna launch a new version of our stainless steel, and actually we're going back to solvent debinding for this metal because we had problems of carbon contamination with our stainless steel done by thermal debinding. So we're going back to acetone debinding for this material. Yes, the presentation should be available as a replay on our YouTube channel. So you just go to NanoE YouTube channel. If you register, you'll have the pop-up when it's available. How tall can a part be printed? 40 millimeter internal diameter, 25, height of 105. If it's just a tube, you should be able to do that. We've made parts that big and even much bigger than that. Again, we would need more information on the printer you're using, the part you're printing, the material you're using. I'm afraid I can't do debug in live. Send us an email and we'll answer to that, of course. Will the H13 still be improved in the future? There is a question about switching it also to acetone debinding, so that might happen, or it's not completely decided yet. Anyway, all of our filaments, we always strive to improve them, so yes, it should be improved in the future. To follow up on that question, if you're testing our steel filament at the moment, I would really recommend testing the new CIS 316L version that is released end of this month, which should really improve a lot the experience both on printing and the binding and sintering. All right, thanks a lot for registering for this webinar and for attending. I hope this was informative. We will have some follow-up webinars. The next one is dedicating to 316L printing, the binding and sintering with our new version of filament. So if you're interested in metals, that might be an interesting one. And we will probably do another one about epsilon printing, because we did notice that a few of the registrants today were interested in the RF material. So we will probably do another one on this. If you have any other questions, you can certainly send them by email, contact us on LinkedIn, on any other media, and we'll be happy to answer. Thank you very much.